in third module, we are going to discuss about normal distribution. So, your normal distribution, we are going to see what is normal distribution, how it works. Example of normal distribution. So, this curve is an example of normal distribution. So, when we are going to have many continuous random variables, so this curve is stating for us the bell-shaped information. So it is having right and left, it is having some sort of values. So somewhat it is throwing some symmetric distribution. So this is the normal distribution. So in other words, the probability distribution of its relative frequency histogram is going to follow some sort of normal curve. So this curve is bell-shaped, symmetric about the mean, and it is defined by mean and standard deviation. So there are normal curves for every combination of mean and standard deviation. So you are going to think why normal deviation is much more important and why it is necessary for our sense of thing. So there are normal curves for every combination. So the mean is going to shift the curve to the left, or the mean is going to shift the curve to the right. So the standard deviation is going to alter the curve spread from the left to right. So the first pair of normal distribution is going to throw some sort of difference. So it is going to have the different means, but it is going to throw the same standard deviation. So the curve in pink color and the curve in blue color is not showing any sort of difference. So the mean and standard deviation is not getting any sort of variation in dissimilarity. So the second curve is throwing some sort of difference. So your pink color is going to hold a smaller value and is going to be taller and smaller. So the standard deviation is very small. So the curve is narrower and it is taller. The probability is spread over a small range of value. So the blue curve has larger standard deviation. The curve is going to be flatter and it is somewhat thicker at the edges. So the probability is spread over the larger range of values. So whenever dealing with properties, so the mean is going to be in the center of the distribution and it is going to hold the highest point. The curve is symmetric about the mean. So the total area under the curve is equal to 1. So as whenever your x is getting increased or whenever the x is getting decreased, the curve goes to 0, but it is not going to touches both the side in flatter manner. So the normal curve is going to be used to estimate the probabilities. So the normal curve can be used to estimate the proportions of population that is going to have certain x values. So we are going to have some sort of standard normal table. So the standard normal table will give the probability associated with the z-scores. So the table will throw the cumulative form from the left to right. So negative side in the table is going to show all the values lesser than 0. So the positive is going to throw some sort of value which is greater than 0. So we are going to have standard normal table. So finding out the z-scores is very important for any sort of given area. So if you're going to have some sort of area and if you want to find out the z-score associated with that area, instead of going with the z-score area, we can go ahead with the area z-score. So we can use the standard normal table to find out the area in the body of values, and we are going to read backwards. We are going to associate the z-score. So using the standard normal table, we are going to search the probabilities to find out an area that is closer to the probability you are interested in. So this is the curve which is throwing some sort of example. So in this we are having some sort of value in terms of z-score, for which the area is holding 5% on right side. Since the table is cumulative, then the left you must have the complement of 5%, and you are going to have the 5%, upper 5% of the area under the moment, which is present on the right side. So this is the normal standard table, which is going to hold the row values and column values. So for 95%, we are identifying which is the row score. So nearing 1.6 is going to be the row attribute. You are going to have the value to be is 0.9495. So Z score of the 95 percentile is 1.64. So the next you are going to identify the area in between the two scores. So to find out Z scores, which is going to have the cumulative limit in the middle of 95%. So the middle 95% has 2.5 on the right and 2.5 on the left. You are going to use the symmetry of the curve, which is 95% in the symmetry. Looking at the standard normal table, which is cumulative from the left, it is easy to find out the area on the left first. So finding out the value of 0.025 on the negative side of the table, our Z score is assured minus 1.96. So in this, we are having till 1.7. So you are going to have the value greater than 1.7. So almost it is holding the value nearer to minus 1.96. So since the curve is symmetric, you are going to have the Z score associated with the area, which is going to have the right side score of plus 1.96. So it is going to be the value in the positive side or right side. So these are some of the common scores. Whenever your reset value is 0.5, you are going to have the associated value to be is 1.64. So your area is between the range of 1.645 to positive 1.645. So your percentile is 90. So likewise, Z is going to be 0.25 means your area association is going to be 1.96. So your range is between minus 1.96 to plus 1.96. If you're going to have hold your Z value to be is 0.005, so you're going to have the value to be is 2.5, and the range of area is between minus 2.5 to plus 2.5. Your percentile information is 99%. So then next one is assessing the normality. So whenever your distribution is unknown and your sample size is not greater than 30 and it is equal to 30, you can assess. So if the distribution is unknown and if your sample size is not greater than 30, you can go with the central limit theorem and you can assess your assumption by using normality. So you're having some sort of mini tab where you can plot your normal probability plot. So this is an example of normal probability plot. Our primary method is normal probability plot. So this plot graphs the observed data. So it is going to rank the data in ascending order. So against the expected Z score of that rank, if the sample data were taken from the normally distributed random variable, then the plot would be approximately linear. So examining the following probability plot, the central line is the relationship where we would expect to see if the data were drawn from the perfectly normal distribution sector. So noticing that the observed data is going to be the dots. So it is representing the linear relationship. So MinTab allows the computation, and the null hypothesis for the test is that the sample data have been drawn from the normal distributed population. So you are going to have some sort of observation. So this is called to be a SNP test. So whenever you are going to the normal distribution, you have to check some sort of confusion. Your normality cannot be assumed in the first sense. So you should always remember that you can do your verification of the assumption. So if your data are not normally distributed, then these probabilities will not be applied. So you have to check if the population is normally distributed. You have to check whether it is large enough to hold a size of n is greater than or equal to 30. You have to remember what is going to be the central limit theorem. You have to construct your normal probability plot to throw the normal distribution value to the researchers. Thank you.